So the last few times we're talking about the algebraic structure of the Gromov-Witten invariance, which turned out to be an algebra over a certain operad, which we interpreted in certain ways. So now we're going to see some different operads which also arise as the algebraic structure of some closed string A models, but in different contexts, which we'll see soon. So let this be the configuration space of k distinct points in the complex plane. Okay. So we define an operad, which is the homology of this space. Homology of the space with k points.
So is k unordered points or k ordered points?
K ordered points.
Do we care what the coefficients are of this homology?
It's going to depend on the, sorry?
Will you reveal them?
Well, it's going to depend on the context. We can start over C, but for example, we saw previously that in the case of Gromov-Witten invariance, the way we were defining algebras over this operad required us to choose coefficients in this Novikov field. But we will see algebras over this operad just defined over C.
But not with integer coefficients, for instance.
With integer coefficients. I'm trying to think about if the definition of the. I think sometimes. I think in the specific geometric example we're going to look at, which is symplectic cohomology, that one could define it over the integers. Yes. So recall that we had these composition operators which had to map like this, satisfy certain compatibilities between them. And this is induced by taking a configuration of points where the ith point is distinguished, and another configuration of points, this time n points, and mapping this to the configuration where we take the configuration of m points, then we take the ith point and insert that configuration into the middle. So this is going to end up being I through to I plus n minus 1, And by relabeling, we'll end up with m plus n minus 1 down here.
So just say again, who was inserted where?
This whole thing
Was inserted in the I spot.
was inserted in the I spot. Okay, so
Something disappeared? There's one less point?
well, this point that was labeled I has been removed and replaced by this whole thing. Yes. Instead of the ith point, we now have this configuration glued in there.
So are the I point is just gone?
Yes.
Well, the ith point is gone, has been replaced by
Right, I understand.
its location.
It's just like it's
No, but maybe you should take little cues. I mean, on a homology level, that thing is an opera, but on the topological level, it isn't.
That's why I defined it as on the homology level.
But why does this give a map on spaces? 'Cause
It doesn't give a map on spaces. That's what Ralph was just saying. But we're only talking about the map on the level of homology of these spaces. And on the level of homology, it doesn't matter how exactly one chose to shrink.
but how is the map reduced on homology and not by a map on spaces?
Okay, well, it's all right. It is induced by a map on spaces, but that map depends on some extra choices of exactly how much to shrink this configuration and then glue it in.
I mean, I thought the problem was that when you do this, the new array of points are not all necessarily distinct. I thought that was the problem.
No, that is
That's
the
not a problem?
that's not a problem. We're starting off with some distinct points here,
Yeah.
some distinct points here.
Yeah, but suppose n is m, and you take these distinct points and the same distinct points here. When you stick it in somewhere, they're not distinct.
Yes.
So it doesn't.
That's you shrink. You shrink this guy down very small so you choose a neighborhood of the ith point and shrink this guy down to be the size of that neighborhood where this neighborhood doesn't contain any of the other points and glue it in there.
Oh my God. But you could write formulas for it. You just take the distance from the ith point to all the other points. Okay, so it just means I completely misunderstood what you said. Okay.
And it doesn't matter how you do this shrinking.
On the level of homology, it's possible to define, to juice up the definition of these configuration spaces in such a way that these maps can be defined on the level of spaces, and one gets an operad in the category of topological spaces, which satisfies all the necessary compatibilities. But the homology you get will be the same. So I'm choosing to work with this simpler version. Okay. And there were some axioms to check that something defines an operad, which basically in this case says if you take the operation of shrinking and inserting, sort of if you've got three configurations and you insert one inside the other, it doesn't matter which order you inserted those three into each other. It's on the level of homology, it's not going to matter. So let's see what this operad looks, algebras over this operad look like. Okay, so we chose to work with C coefficients. So of course, zeroth homology is just a one-dimensional vector space. first homology is also one-dimensional, generated by the one cycle in this configuration space where the 2 points rotate around each other. Or explicitly, Z1 is at 0, Z2 equals e to the I theta, theta between 0 and 2 pi. These two operations generate the operad P. The class in H naught corresponds to an associative product okay. By the same argument as before. The associative operad, which is just a one-dimensional vector space in all degrees with identity maps as composition maps. And this maps isomorphically to the degree 0 homology of our configuration spaces. Okay, so what this is saying is any algebra over this operad P has an associative product induced by this class, the class, the identity class in H naught of this configuration space. Okay, but now we have another operation with two inputs coming from first homology of this configuration space, corresponding to rotating one point around the other. So we have more than just an associative algebra. And this corresponds to a Lie bracket. So if we're saying it's a Lie bracket, it has to satisfy the Jacobi identity. So we need to see that. Let's write out the Jacobi identity. So this corresponds to a homology class in H2 of configuration space with 3 points, which corresponds to taking the first and second point, rotating around each other like this, and then putting those inside a little bubble which is rotating around the third point in the space. Right? So that's what happens when we take this class in H1 and applied to the first two guys. That's this Lie bracket in A and B in the first and second inputs. And then apply the same thing again to the result of that bracket, taking the Lie bracket with C. Okay, so this gives us a 2 cycle. Now we want a similar thing. Where we have the second and third guys rotating around the first guy, and the third and first guys rotating around the second guy. So let's call these cycles C1, C2, C3. So explicitly, we can write out what this 2 cycle looks like. This is homologous to the picture I drew there, if we just decide to keep Z3 fixed. Where epsilon is much less than 1. Now, and similarly for C2 and C3. Now we're going to try, yes, again. We're going to try to define a 3 chain whose boundary is C1 plus C2 plus C3. So we're going to define it by this formula. Okay, so we're starting, so at t equals 0, we have exactly this chain C1. Where Z3 is 0, Z1 is e to the I theta 1, Z2 is e to the I theta 1 plus epsilon e to the I theta 2. That's this chain here. And now we smoothly change the radii where we're putting this Z1 and Z2 in such a way that we end up at t equals 1 so at t equals 0 we get C1. At t equals 1 we have Z3 equals 0, Z1 and Z2. Z1 is epsilon e to the I theta 1. So Z1 is going around Z3 in a little circle. Z2 is epsilon e to the I theta 1 plus e to the I theta 2. So this Z2 is effectively going in a big circle around these little guys going in a little circle here. So one can turn this into a proof that the t equals 1 boundary of this cycle we've defined is homologous to C3. Okay, so we've defined a cycle with boundaries C1 and C3, but it doesn't always lie in our configuration space. When these two auxiliary functions f and g cross, we may have Z1 equal to Z3. So remove a neighborhood. Of these points. The boundary of this neighborhood is homologous to C2. Okay.
So A, B, and C are in the homology of B3.
No, so we were so we recall that algebra over P is a vector space V with maps P of K to Hom V tensor K into V. So A, B, and C represent elements of whichever vector space we've chosen to define our P algebra structure on. And what we're proving is that anytime we define such a structure, the Lie bracket we define by taking the class in H1, conf C2, that gives us some class in homology here. We map that to here, so that gives us a map V tensor V into V, which is our Lie bracket. And we're proving that bracket automatically satisfies the Jacobi identity, just coming from the structure of the homology of these spaces.
So what are A, B, and C?
Sorry?
So what are A, B, and C?
A, B, and C are elements of V. but somehow what we're proving is you should really imagine A, B, and C as being blanks, and what we're proving is really about the operation bracket rather than about any particular algebra. Right, so we remove a neighborhood of the points where Z1 equals Z3.
In the image of your map.
Yes, in the image of this map here.
So you're removing something inside the configuration space or inside the domain?
Inside the domain here. Yeah. So that after we remove that guy, it actually maps inside configuration space. Okay.
So I correct that in the end now we have an associative product and a Lie bracket.
Yes. But these also satisfy an extra compatibility between them.
Do you have a grading on, I mean, your homology operator is actually graded.
Yes.
And you assume the same for B, and this is a graded map.
Yes.
So, that's the green one. Yeah.
That's right.
It's very worth observing that this isn't quite.
Right. So
The signs in this thing are not going to be what you expect.
that's correct. It's the bracket. Okay. Comment on gradings. So if we equip V with a grading such that these maps, giving the structure maps of our P algebra, are Z graded maps, then the algebra, the associative algebra product is going to be graded because it comes from a class in H0. So this will turn into a degree preserving map from V tensor V into V. And, well, super graded commutative. The Lie bracket gives a graded Lie bracket on the shift. Rather than on the vector space with the original grading. That's because...
I'm confused by we make. Is an algebra over an apparat always graded by definition?
No, not always by definition. I mean, it's possible to have other notions. But in this case, all the cases we'll look at will be at least Z mod 2n graded.
Okay. So we're interested in the graded case. And so
Yes.
What is your convention for the shift? If I put a brackets 1, do I shift the complex to the left or to the right?
nobody can figure that out.
It makes the Lie bracket have degree 0. Okay. 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 So there's one other compatibility between this associative algebra and this Lie bracket. Which is called a Poisson type identity. Right, so when so here I'm really writing the algebra product when I'm writing things next to each other. Okay. And then proposition, this is a complete set of generators and relations for this operad. Sorry?
What's the A with the two vertical lines?
Sorry. This is for homogeneous elements of degree that means the degree of A. So the grading.
Be operating in a graded setting.
Yes. At least Z mod 2 graded. Yes.
Nothing like this holds. If everything's concentrated degree 0, then the bracket has to be trivial. Because you bracket
Yes.
two things together degree 0, you should get something of degree 1, and then there is no such thing.
Well, I mean, one can also work with Z mod 2 coefficients. In some contexts, that's all you can do, and sometimes that's useful as well. This. Okay.
But if you work with mod 2 coefficients, that doesn't mean you can make sense of it.
Well, it just means one doesn't have to worry about this sign. It's the same whether it's plus or minus.
I think you also meant your thing might just mean actually Z mod 2 graded, and this is interesting in that context as well? Or
No, what I was trying to say is that if here one took homology with Z mod 2 coefficients and worked everywhere with all our algebras are algebras over Z mod 2, then signs don't matter. And this identity will hold where we don't care if each term is plus or minus, so we just forget about it. Okay. So the proposition is that this is a complete set of generators and relations for this operad, i.e. to give a P algebra is equivalent to giving a product and bracket satisfying these relations. Whereby these relations, I mean the Jacobi identity and associativity of the algebra and the this Poisson type identity, as well as the required commutativity of the product and bracket under reversing the order of inputs. Sorry?
What's the last one you said?
The fact that the algebra product should be graded commutative. That was part of the equivariance of these maps with respect to permuting the inputs. And similarly, the Lie bracket should have some graded anti-symmetry. Okay.
Sorry, I missed the beginning. Are you looking at a special class of operands that are associated to these homological configuration spaces, or are you saying that
This is one operad. Well, up to all our choices of coefficients, yes. Yeah, it's the operad, which is configuration space of. It's one specific operad, yes. So algebras over this operad are called Gerstenhaber algebras. Okay.
Are there examples where you can sort of see geometrically where there's obviously an algebra over this operand?
Yes, that'll be the very next thing we'll do. So first, there's an obvious map of operads from this homology of configuration space to homology of M bar 0 k plus 1, which we saw the Gromov-Witten invariants were an algebra over this operad. So in particular, Gromov-Witten invariants automatically give, cohomology of M, coefficients in lambda naught, the structure of a Gerstenhaber algebra, but so this map is defined by regarding C as CP1 minus infinity. So we have K marked points on C, therefore K plus 1 marked points on CP1, therefore an element in here, but one that avoids all the boundary divisors. But this is somehow not very interesting because first homology of configuration space maps to first homology of this space, which is trivial. In particular, the Lie bracket that we get on the cohomology of our manifold from this construction is always trivial. So we only see, from this construction, we only see the associative product, which is the small quantum cut product. Okay. But we will see, my plan is next lecture to talk about some examples of closed string A models in which we naturally obtain a Gerstenhaber algebra structure on our theory, in which the Lie bracket is non-trivial. So, and that will be symplectic cohomology. So that will be something different from Gromov-Witten invariants. Okay. So now, let me tell you finally about what appears on the other side of mirror symmetry. The closed string B model, and we'll see that this naturally has a Gerstenhaber algebra structure. So let M be a complex manifold, or alternatively some algebraic variety. One part of the closed string B model is the tangential cohomology, which is our name for this object. The cohomology, in the sense of sheaf cohomology, of the exterior algebra on the sheaf of holomorphic tangent vectors, tangent vector fields to our manifold. So we call this exterior algebra on the tangent sheaf of tangent vectors, sheaf of polyvector fields.
Holomorphic sections of that whole.
Yes, holomorphic, yes. So this sheaf of polyvector fields is naturally a sheaf of Gersten-Haber algebras. Okay. So the product, associative algebra product, is the exterior or wedge product on the exterior algebra. So that's, I mean, this is clearly has an algebra structure, and that's what that is. And the bracket is less trivial. It's what's called the Schouten-Nijenhuis bracket. So the bracket of two vector fields under the Schouten-Nijenhuis bracket is the same as their Lie bracket. And the bracket of a function, just a holomorphic function with a vector field is just evaluating the vector field on the function, differentiating in the direction. Sorry.
Sorry, the upper one of T star M
Yes,
is a vector field, not a covector field, is that right?
that's right. It's a vector field. This is
I thought putting the star up there you were dualizing.
no. I was just meaning to indicate. I don't know. Maybe I should put a bullet instead. It's just to indicate a.
Better put the star on the lower.
Yeah.
Oh, okay. Sure. Want me to do that? No?
Oh, below it's not a two form, it's a field of planes.
That's right. It's yes, exactly. So let me leave it like that. I think we
You could
understand.
explain this now, though? You can explain why it's naturally a sheaf of Gersten-Haber algebras?
Yes, that's what I'm explaining. That's what I.
But this should somehow. Okay, go ahead.
All right. So. So giving these two conditions on what the Sheridan-Ninehouse bracket is on low degree polyvector fields, determine it uniquely. Via the Poisson identity. Which we recall, well, is this one here. So once we know what the bracket looks like on the lowest degree things, we can upgrade it to knowing what it looks like on products of those things together using this relation here.
The bracket of two functions is
0. Yeah. Yes, I should have written that. So one can write this out explicitly. So if we have a bunch of vector fields that we're wedging together, then their Sheridan-Ninehouse bracket is sum of -1 to the I plus j. I think that's the correct sign. So, yes, one by working inductively through from these guys together with this relation, one can define the bracket of any two polyvector fields which are a wedge of holomorphic vector fields, 1 through m and 1 through n, and it looks like this. And then, I mean, from this formula, one has to check that this relation is really satisfied and the Jacobi relation is satisfied. That's, well, the only way I did that was by plugging it into this formula. But
It's okay because your algebra is free on something in degree 1 or -1, and then it really is enough to just specify it and expand according to the rules. So you specified it on the generators.
okay, all right. So maybe I didn't have to do as much work.
If you got unlucky and your sheet was not free on the generators in a single degree, then you have something to prove.
Okay, all right. So maybe I did the stupid verification then. Okay. All right. So we have this exterior product, this Sheridan-Ninehouse bracket, and these together make the structure of a Gersten-Haber algebra on this sheaf. And it follows that the sheaf cohomology of this sheaf is also a Gersten-Haber algebra. Okay.
I want to be clear, but it makes
Yes.
So, if I give you a cycle of points in the line, can you give me a intuitive description as to what that does to one of these holomorphic guys? Or is it?
I can't. No.
This is all.
Sorry.
Okay.
I guess I've always well. I would like it if there were, but I've never seen anyone give any explanation like that in the literature.
And does the gradient be by HP of which Q?
Good question. It's the sum of it's P plus Q. Yes. Okay, and now we're going to define a slight twist on this. So a name that we've inherited from physics, a Landau-Ginzburg model M, W is an algebraic variety. I believe it's in all cases I know it's smooth. In all cases, I know mirror symmetry applies to it smooth. M with a holomorphic function on it. Which is this W. And this W is called the superpotential. Again, coming from the physics literature.
So then it's probably not compact.
No. Right, well, yes, never. Never, presumably.
Well, W could be 0. I mean, is that interesting?
No, well, I can, no, the point of the B model on a Landau-Ginzburg model, it's meant to be about the singularities of W. So in both closed and open strings, there is some theorem along the lines that whatever version of the B model you define, it only depends on a formal neighborhood of the singular points of W. So if we've got one of these guys, which frequently come up as mirrors to honest, smooth, symplectic manifolds, we have to define what the analog of this sheaf of polyvector fields is. And it's the cohomology of the same thing, sheaf cohomology of polyvector fields, but with the differential Schouten-Nienhaus bracket with the superpotential W. All right, so So because of this fact that functions, when bracketed together with the Schouten-Nienhaus bracket, give 0, bracket with W is a differential, and okay, because that and the Jacobi identity. Okay. Right, so maybe I should just write it out. So we get some signs here. So all other terms in the Jacobi identity will involve W bracketed with W, which is 0. So this is a differential. Furthermore, the Jacobi identity says that okay, so I'm sorry, I'm not writing signs here. So this can be written as a version of the Leibniz rule. Which means the bracket descends to this cohomology.
See your this calculation that it's a differential.
I'm
Why do you get two terms with W bracketed with it?
oh, I'm sorry, the 2 goes on the other side. Right, yes. 2 of these guys gives this guy.
I expect them to be with opposite signs. Or is it something because it's some great as well, I expect.
Okay, it's because, all right, the reason it doesn't come out the way you would expect is because W is in degree 0, but as we saw earlier on in the definition of a Gerstenhaber algebra, the Lie bracket is on respects degrees in the shift by 1 of the grading. So W is odd as far as the Lie bracket is concerned. And I think, well, okay, I really should have written out the Jacobi identity with its signs in my notes, but
It's just like the Homological equation. If you ever look at the Homological equation, and then we simplify it. But it's right, it's just because the degrees are shifted.
yeah, okay. Sorry, I didn't, yeah, I should have prepared that.
You do homology twice in 2 different ways. Always confused why you might not just say, take your exterior algebra on TM, put this bracketing with W on it, that's a sheaf of C-lin or CDGAs, and take hypercohomology of that. So you sort of take
Oh, you mean differential greater than?
Yeah.
I mean, thinking of bracketing with W as endowing it with some kind of differential. It's not linear, but it seems linear. Yeah.
So I guess, yeah, I guess, I think in all the cases I know M is affine, which probably means these two things, well, at least there's a spectral sequence in which the E2 page is this guy leading to the thing you were talking about, and probably, but I haven't seen that definition. I don't know why it should be this rather than that. But perhaps in the affine case they're the same thing anyway, which is, I think, no, it's not all the examples, but yeah. So I'm not sure of the answer to the question. Sorry, what is?
It is linear. I said it was not linear, but it is.
Okay. So also, Poisson identity implies that this differential we've defined is a derivation with respect to the algebra structure, the associative algebra structure. So that also
On what? Derivation of what?
what it means is for all U and V in here, dW, this is bracket with W, of U times V is dWU times V plus, again, assign U times dWV. So this algebra also descends to the cohomology. So we really do obtain a Gerstenhaber algebra structure on the cohomology of this. So an example that's particularly nice, if we're working over some field and our variety is just affine space, n-dimensional affine space over our base field, W will be some polynomial in n variables, then this cohomology is just, well, this is affine, so we just get exterior algebra over our ring to the nth power. So or should I write this a different way? Where it's also a polynomial ring in n commuting variables and n anti-commuting variables. And the Sheridan 9-house bracket with W is the same, turns out to be the same thing as contraction with the differential of W. So we get a Cazul complex for the differential, the partial derivatives of W. So that's a particularly nice case.
You described two cohomologies. The one was the Schiffer vector fields, and the other was this Landau-Ginzburg cohomology. Which of the two is the one you just said?
What I'm saying here is that in this case, this complex of which we are taking the cohomology is a Cazul complex for the
Cohomology is trivial, then, you're saying?
No, if W has some singularities, then we actually get non-trivial cohomology. Right, it's just global sections, yes.
W is the first coordinate.
Yes. So if M, some symplectic manifold, is mirror to M check, some algebraic variety, respectively M check, W check, some Landau-Ginzburg model, then the small quantum cohomology should be isomorphic to this tangential cohomology, respectively the tangential cohomology of the Landau-Ginzburg model, if the mirror is one of those. As algebras, In fact, as Gerstenhaber algebras, we saw earlier that on the quantum cohomology side, the Lie bracket we naturally got was trivial. So in fact, mirror symmetry predicts when we have quantum cohomology as our A model, the Lie bracket on this tangential cohomology is trivial. We only have the algebra structure as the relevant in this part of mirror symmetry, in this context. Yes, so so why would this Schouten-Nienhaus bracket turn out to be trivial? Well, if we have some holomorphic volume form, this is some N0 non-vanishing N0 form. Then contraction, so should really write M to be consistent with earlier. So if we have a holomorphic volume form capital omega, we can define a map from tangential cohomology, this is polyvector fields, to cohomology of holomorphic differential forms. That's omega star of M. And this map is defined by taking alpha in here and contracting it with our N0 form living in the top degree part here. And in fact, this is going to be an isomorphism. So let's say smooth complex. Manifold. Okay. So let delta, which is a map from should be -1. So we take the Dolbeau resolution of holomorphic differential forms on M. So the differential here will be the del bar operator on forms. cohomology of this gives us cohomology of our holomorphic differential forms. But then we also have another operator, which is the del operator. And on identifying this cohomology with our tangential cohomology via this map, we pull this del back to delta on tangential cohomology. Then we have a lemma due to Tian and Todorov that that in fact the bracket satisfies an identity that looks like this. Okay. Yes. That's, well, I won't have time to say that this time, but yes, this an operator delta like this, which satisfies this relation relating the product and the bracket, and furthermore delta squared equals 0. This equips our algebra with the structure of a BV algebra on top of the Gersten-Haber algebra structure, some extra structure that exists. Okay, so we can get the bracket in terms of the product and this delta that is pulled back from the holomorphic differential on PQ forms. And this is something that can just be proved locally. So if M is compact Kähler, then the Hodge to de Rham spectral sequence, also called Fröhlicher, degenerates at the E1 page, which is another way of saying that the differential on the E1 page, which is the holomorphic, well, this vanishes. And in particular, we get this Hodge decomposition of the de Rham cohomology of our manifold M. But now this delta that we defined here is the pullback of del under an isomorphism between tangential cohomology and cohomology of differential forms. So that also vanishes, which means that the Schouten-Nijenhuis bracket vanishes by the Tien-Todorov lemma that I just put up there. So in fact, if M is a compact Kähler manifold admitting a holomorphic volume form, then automatically this Lie bracket vanishes, which mirrors what we saw on the quantum cohomology side, that the Gerstenhaber algebra structure naturally defined on here had vanishing Lie bracket. So I think that's the end of my time. So yeah. Any questions or? Okay.